All right, so we are getting into potential energy. Those of you who are watching this online, you'll get a nice treat because I'm starting this before the class is actually ready. So I'm going to continue with this because I've got 2 lessons to go through. So whether the class is ready or not, I'm going. So potential energy. Potential energy is energy that is stored. So if you put energy into an object, it has the potential to do something. This is in your note package. You should have your note package out and you should be writing all this stuff down. You'll find out.
Mister, we took potential energy last year.
Good. And kinetic as well, right? Because those are the 2 that I'm covering today. So for example, elastic potential energy. We've talked about this already. So if you compress a spring or stretch a spring, you're giving it potential energy. It has the potential to expand if you compress it, or if you expand it, it has the potential to compress. So you can often with toys that launch something, they have some sort of a spring that launches them. So this is one type. We can also have chemical potential energy. Any ideas of what could be an example of chemical potential energy? T's doing an excellent job of doing this right now. Same with Hetem. Chemical. There is energy stored in food. So when you consume, those have a little bit less energy. They're not as good as what they're eating. But there's also some other types. This burger looks so gross in my opinion, but
I agree. What's the
there's some pickles in there. There's mustard, ketchup, onions, and it looks like an uncooked burger. Batteries. They have chemicals that are inside of them, and they have the potential to charge whatever electronic object you're dealing with, or gas that you put into your car. So it has stored energy inside of it. When you consume it, you take the energy from that and it gives you energy. We're going to get there. It's like you're reading ahead in the notes or something. All right, electric potential energy. Where does baby get the energy from? Oh, burger. I heard baby. Well, it's just in the nutrients of the food. Yeah, so bread, you get it from the wheat or whatever it is. Burger from your cow. Cow gets the energy from, well, I'm assuming that meat's from the cow. I don't know what it's from. So you can have electric potential energy. This is the energy stored in a cloud. So if you don't know how lightning is produced, you have electricity that builds up in a cloud, and when it gets enough energy stored up, it cannot contain that energy anymore, so it releases it as lightning. So the main one we're going to focus on is gravitational potential energy. And this is the one you've seen last year. This is stored energy due to an object's position on the Earth. So this lady here holding up the barbell here, that barbell has the potential to do something. What does it have the potential to do? To drop, fall. So when you lift something up, you give it some potential energy. It has the potential to fall. So everything that's on my desk actually has a potential energy. Because if I were to remove the marble from underneath it, it could fall. Do you have potential energy right now? Yeah, because if someone so conveniently kicks out the chair from underneath you, you're going to fall. So here's the question. How about the desk? Does the desk have potential? If you remove the floor. How about the bottom floor? What if you're at the center of the earth? Does that have potential energy? Relative to what? It could go towards the sun. Does the sun have potential energy? Where could it go? Center of your universe. Yes. By the smirk on your face, I feel like this is going to be an interesting question. Yes? It still has yeah? So, have you ever owned a helium balloon? What happens over time? Yes. And when you throw it away, does it stay in the garbage can? Yes. Every helium balloon ever released always goes towards the sun. That's exactly what happens. So it has the potential to go towards the sun, is what you're saying. Ah. Okay. So remember with this, so for this lady, when she's lifting up the weights, she's doing work on an object. So this is just in a recap kind of yesterday. So energy can be transferred, and this is by doing work. So this is how it relates to what we talked about yesterday. In yesterday's class, if you didn't watch the video, we talked about work is a change in energy. So when you change an object's energy, you do a work on that object. So by taking something like my water bottle, if I lift it up, I give it more potential energy. So therefore, I'm actually changing the energy in the bottle. For those of you who did the science experiment today with the potatoes, you are doing work on the potatoes. Was it just you? Oh. No one else in this class was roasting potatoes today? No. Lucky you. You are giving the potato energy when you heat it up. Okay. So work converts energy into different forms. Have any of you ever watched Wile E. Coyote from the Looney Tunes? Okay. The physics in this is totally real. All the time. So if you have this situation, this rock up here has the potential to fall. Right? So there can be work done on this object and it falls. Have you ever watched it? He runs off of a cliff. He doesn't fall until he looks down. And that's exactly how gravity works. Yeah. Yes, I know. I'm overly sarcastic at times. It's called a very dry sense of humor. What's that? Yeah, you don't always, not everything's going to be in the boxes. But this is just an example of this. So you can think of potential energy as the potential to do something. When we're talking about gravitational potential energy, it's often the potential to fall. Because that's what potential energy due to gravity talks about. Yeah.
So let's say now that the older thing is on, like let's say this thing
Yeah.
if it was a smaller, like if it was a smaller clip that was holding on, would it have a higher potential and then a high potential?
So you're saying if this that's supporting it is smaller, does it have less potential? No. So potential energy just has to do with how high it is. So it doesn't matter about what's supporting it, it just matters how high. So the higher this boulder is, the more potential energy it has. We'll get to the equation in a second. Because it has the potential to gain more energy when it falls. Yeah. Well, it's not that it accelerates faster, it's that it accelerates longer. And once we get into kinetic energy, I'll show you the relationship between those.
Isn't there like a certain point where it reaches like maximum velocity? What would happen like to the potential energy then? Like when you jump the thing when you jump up going off the Empire State Building, it's like jumping it from the 20th floor.
Yeah. So in talking about terminal, let me get through potential energy, and once we get into kinetic, I'll talk about that specifically. Yeah. All right. So here's the equation for it. Does this look familiar? This was from yesterday, yeah. Good, that shows that some of you are watching the video from yesterday. So this is your equation for potential energy. Mass times the acceleration due to gravity times the height. So the amount of height you have tells you your potential energy. Once you have the force of gravity, which is mg, times it by the height, that tells you how much potential energy you have. Yeah, so the one yesterday was very specific because it was talking about you need to do work, you need to change the height. So with work, if I'm simply holding this object here, I'm doing no work. I'm doing no work on this object right now because I'm not actually moving in a distance. However, it's at a height, so this still has potential. But I'm not doing any work on it until I move it. So the distance from yesterday's notes is more about a change in distance, whereas this is just at a specific height. I already said this. I forget if there's a... What's that? There should be a spot, I think, on your notes. Is there a note? How about the box beside that or underneath that? Okay. This one? So gravitational potential energy is always measured relative to some reference point. So this is kind of what I alluded to when we talked about what object has potential energy. Because depending on where my reference point is, some objects have potential energy and some do not. So for instance, we said the items on my desk have potential energy. Because if I remove the desk, then they're going to fall. But if I said, what's their potential energy in reference to the desk? The height is 0. Because the height above the desk is 0. But if I said, what's the potential energy of my laptop from the first floor? So then I've got a height. So if I am talking about a height, I need to give a specific point. So everything has potential energy because we all have a height from something. There's different reference points where I can talk about it. So if you're ever asked, does something have potential energy? Relative to what? So when you're given questions, you need to look what is it in reference to. So I will often in a question write, what is this object's potential energy above the table, or above the ground, or from this point? So you need to know what is your reference point. So if you're saying what's it relative to the table, there's no height. If you say relative to the ground, you have some height. Oh, yeah. Because the table, I thought you meant from the tabletop. The table is resting on the ground, so it's not above the ground. Therefore, its height is 0. Hetem, did you have something to add? Yeah, it just refers to where the reference point is. So I can tell you that these items have a potential energy from the ground without having to remove the table. Because it's just the height is relative to the table. Or from the ground.
So if it's on the ground, it's 0.
Yeah.
But if it's on the table, it's the height of the table.
Yes. So let's look at this. So if we have a textbook sitting on a table, so here's your textbook sitting on a table. If the book is lifted 0.8 meters above the table, so it goes from here, it gets lifted up to some distance above the table. We want to know how much gravitational potential energy does it have, first with respect to the table. So in order to do that, potential energy equals mgh. We have the mass of the textbook. It's 15. That is one heavy textbook.
So what is it like to the ground or 1.8?
So we're on the Earth. And the height I want is relative to the table. So we're told we went 1.2 meters above the table.
No. The table is 1.2 meters.
Good. So 0.8. You caught me even before I could trick you. That's good. So 0.8 above the table. And then calculate this, get a number. 178.6? What's my unit for energy? Joules or Newton meters or kilograms meters squared per second squared? Nope. Newtons are a force. Energy is not a force.
Newton meters are okay.
Newton meters are okay. NM. No difference. J, just use joules. Joules is the most common for energy. So what if I asked you instead, what is the energy with respect to the floor? So what changes? My height. It's no longer 0.8. I need to make it relative to the floor. So this is 0.8. This is 1.2. So this whole distance is 2 meters. So we have the same equation. Oops, same mass. What did you get for that?
294.
So be very, very careful with this. I can trick you with many different distances. You need to think, what is your change in height? Or not change in height, sorry. What is the height relative to? So make sure you're paying attention to what is it relative to. Where does the 2 come from, or where does the 9.8 come from? So 2, it says I want respect to the floor. So my height needs to be from the floor to the textbook. Yeah. Any other questions of this?
Yes.
We've got, this is section 2 out of 7.
7.
Yeah. Today is really easy because you've already seen these before.
Yes.
That's why it's easy.
I've never seen that program.
You will find out what we'll take. So, here we've got an archer pulling back on a bowstring. Have any of you ever shot a bow before? Just a few of you? Okay. So, I used to teach archery at a kids' camp over summer. That's why I'm asking. So if you pull back on the bowstring with 240 newtons, for a distance of 0.2 meters, we can calculate the potential energy on this system. So, the bow arrow system, like looking at the bow, what am I doing here? So, the question with this is potential energy. Potential energy we just said is mgh. But we're not dealing with something being lifted up. So the problem with this is we're now dealing with work. So what is the work that I'm doing on this? So what we're going to need to do with this is, let's see. So work is equal to two things. Force times distance. What else? No. It's also equal to change in energy. So in this system, what we've got, we're told the force that you're acting on the object. We know that's 240 newtons. You're told the distance that you apply this. What kind of energy is changing in this question? Potential energy. So I'm dealing with this. I want to know what is the potential energy that I have by doing this. So force times distance equals change in potential energy. So Fg, change in potential energy. Change in potential energy is just energy potential final minus energy potential initial. If you haven't pulled back on the bowstring, there's no potential energy. So this is 0. And I'm looking for what energy potential final is. So it's just force times distance. Full 24, so 48 joules. Is it 48? Good.
Did you cross the equal?
Because it's 0. So, yeah. So if I haven't pulled back on the bowstring, there's no potential energy here. It's not going to do anything. It only has potential once you actually pull it back. Yeah.
What is this with respect to technically the law of energy of the rock?
So, remember with potential energy, it's a stored energy. So, and when we need to look at if something is stored, it has the potential to do something. So when my bowstring is relaxed like this, there's no potential energy. You leave a bowstring relaxed, it doesn't do anything. It has 0 potential to do anything. Whereas when I pull it back, relative to this equilibrium position, now it's got some stored energy. So that's why when it's at rest like this, there's no potential energy.
So, yeah, because it's a bow, it would be pretty obvious that we're looking for the potential energy of the thing.
Yeah, yeah. And the only one I would give you is something like this is with force and distance. I can't do mgh because you're not dealing with something working against gravity. It's just like this. So that's actually a good question. So I said there's always potential energy. So with this bowstring, there is potential energy. If you've ever held a bow, it's actually still bending the, I don't know what technically this part is, the bow without the string. So it's still bending that part. So there is tension in the string. So there is a potential there. But I'm going to say this is my relative point, or my reference point. Relative to rest, what is this new distance?
So Mr. Start from here,
Yeah?
not from rest.
Yeah, so then there would be a different distance that you're pulling back at.
And we solve for distance by doing algebra.
Yeah.
Isn't there like always gravitational potential energy?
Yes, but in both of these situations, it's the same. So that isn't the potential that's changing.
So Mr. The EPI will change if we start like from here.
Yeah, so depending on where your reference point is, I said this is the reference point. If we talked about the bow being slightly bent like this, then your distance is different. Then it would be relative to this new initial position. What's the final? Are we going to use three big equations? Yeah.
Yes?
I did yesterday.
What's the formula that you use to get the 240 times 3?
Force times distance. Yeah, I just switched this around because I'm solving for EPF. 240 force, 0.2 is the distance it's pulled back. Yeah, so this is just, so change in potential energy is the final potential energy minus the initial potential energy. So this is my initial situation is I had 0, and here's my final position where I have some energy. Yeah. Yeah, because delta just means change in something. Is the hint on your sheet or no? Is this hint on there? Okay. You can write it out, but I kind of already did it.
Mr. London,
Yeah.
the question said that the boat said.
So not the string.
Yes, the boat said. So we use the other equation.
So in this case, there's no change in height.
Yes, but there's going to be a mass.
Yeah. Yeah. But then we'd need to talk about where's the center of gravity, because am I talking about this height, or this height? We'd have to consider center of gravity, and it gets more complicated. So I wouldn't give you something like that. There you go. So that's potential energy. It's 11:32. So what I'm going to do is I'm going to give you